All right, so today we are going to talk about sorting. And what's actually going to happen after the lecture, I'm going to go and post the assignment 5, I guess we're up to, assignment 5. I think you guys will like this one. It's not necessarily hard. There's 3 parts to it. You basically have to do 3 different algorithms, sorting algorithms, kind of on your own. Like you got to code them from scratch, basically. But it will not be, the setting up the assignment itself is not the hard part. Hard part is like picking the right sorts to do. But we'll talk all about those details probably right at the end of class about the next assignment. OK? Any questions before I get going about the class, about other stuff that'll be due? It will be due, let's see, November 14th, which is like a ways from now. I am going to try this. I'm going to try to say no extensions, which means if you think you might need an extension, then you've got an extension until the due date. Right? Like in other words, consider your own extension early. Like consider your own deadline rather early. Like not Friday, but like Tuesday. And then if you think you're going to need an extension, think, oh, I've got an extension all the way until Friday, which is really just the real deadline. So does that make sense? I mean, I'm just trying to limit the number of extension requests. We'll see if it works. But basically, I'm just going to say no extensions and see how it pans out. OK, here's what we're going to do today. First things first, I'm going to show you a little Unix tip of the day that I think is it's a little different than the other ones I've showed you. And then we're going to talk about sorting. And sorting is kind of a big topic. But we're going to talk about 4 particular sorts today, and then maybe 3 or 4 on Monday as well. OK? All right, first things first, the Unix tip of the day. Turns out there is a mail server on Linux, which means that you can actually send mail from the command line. So let's say you want to send yourself, let's say you email me and you say, oh, my function doesn't work, blah, blah, blah. And I say, well, why don't you just send it to me? There's other ways to do that too. But you could just mail it to me as an attachment if you want. Let me show you how that works. OK, if you type mail and then -s for the subject and then an email address somewhere, right, you can actually send an email like that, right? So let's see if we can get this to work. Here we go. OK. Let's go into homework. OK, mail-s sorting algorithm help. Let's see, pres@whitehouse.gov. OK, and then you hit enter, and you can start typing the actual text of the email, right? Dear Mr. President. Dear Mr. President. Could you help me with my sorting program for Comp 15 at Tufts? Thank you in advance. Your humble compatriot, Chris. OK, so then you do that, and then you actually finish the email by doing Control-D, which happens to be a kind of a standard Unix way of ending like something that you're doing in the terminal. Control-D, and then it says end of text, and it's gone. And so now if there happens to be an email address at pres.whitehouse.gov, then I don't know, I'll probably get an email later saying, please report to the following police station, blah, blah, blah. So who knows? Anyway, that's how you do it, and it's simple as that. Do you guys know Bruce Mollet from Comp 11? He did a bunch of stuff with Comp 11. He uses this all the time to send emails, which is why sometimes your email is just like plain old text from him, and it's like this is why, because he just does this and you know, has an email like really quickly. OK, so that's how you send a regular email. Let's say instead you want to actually there's some sorting stuff. Let's say that you actually want to let's say you want to send it with an attachment. You can't use the mail program. You have to use this other program called MUT, which stands for mail something, 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 I guess. Anyway, you do it like this. You say MUT-X, which basically says I'm going to type this in a special window. -S, which is the subject, the email address, and -A, and then that's the attachment you put in there, whatever your attachment is. It's going to be any kind of file, right? So let's see. mutt-x-s, why didn't you help me? Right? And then -a, I think I have a folder called lab6, or a file called lab6.zip. And then this actually gives you, oops, I forgot to put the 2. But it'll ask you. If you forget to put the 2, it'll ask you. Let's see. barack@whitehouse.gov. How about at mrprez.gov, something like that, right? Okay, and then you actually, this one's a little bit different. You have to say, you have to end your file with a period. It tells you on a line by itself. I'm not sure why, but hey there, I failed my last assignment because you didn't help. Why? I've attached my grade report. Whatever, right? Chris. And then a period on its own line, and then that sends it along. Right? So that's that. And then you've just sent an email, okay, to the president, who's actually pretty good at computer science, turns out.
Really?
Hey. He's going to help me. Oh. Well, now he's going to get me. Now he's going to get me arrested, but you know. Okay, questions on mail or mutt? Any questions? Yeah.
Seen that video on YouTube is pretty popular.
Yes.
Him being asked a question.
Yes. I'm going to show it to you in a few minutes.
Okay.
Yeah. So you're stealing my thunder. Thank you. Yes, I have. So I'm surprised nobody's asked this yet. I did that from my Linux CS account. What's your question? What's the sender email? Yeah, where's it come from? You actually have an email account on the CS server. So if you go to no, it's not www. It's webmail.eecs.tufts.edu, and it will probably say the certificate's bad, but I don't know what's up with that. And then you can actually log into the actual web server, and it will give you all your email. Right? So like that. And that's your email. Now, you probably don't have any. But what you could do is you could either start using that email, which you probably don't want to do. But if you wanted to, you could. And you could forward from that email to like some other email if you wanted to. Anyway, this is the one I actually use. So if you send an email to, what is it, christopher.greg@tufts.edu, that gets forwarded to my other one, which is fine. In fact, I get a weird like double forward. It's kind of weird, but anyway. OK, questions on that? Yes, Alice. Squirrel mail. Yeah, that's the name of the program they use. No, it's not a Tufts thing. Then it'd be jumbo mail or something, wouldn't it? Oh, dead squirrel, yeah. No, dead squirrel mail. That would be weird. No, it's not. No, it's a commercial program. Yeah. Okay. All right. Let's start talking about sorts. Okay. So sorting is it's a very necessary sort of thing we need to, no pun intended, thing we need to do for computer science, right? Why might we want to sort things? Like, what are some of the use cases for sorting things? What do you think? Do you think we ever need to sort anything? No, we don't need to sort anything. Let's all go home. Why would we need to sort something? Like, any examples? Yeah, Cecily. If you want them in order. Right, but what kinds of, I mean, we want a lot of things in order, right? People are generally like have ordered minds, and we try to have, like, putting things in order is a good thing from the standpoint of, is that you or me? I don't know if that, putting things in order is necessary for a whole bunch of reasons, right? I mean, how about, we've already talked about when putting things in order helps from data structures. Can you give me an example of that? Finding things easier, right? If things are in order, right, we can then do a binary search, unless it's a linked list or something silly like that. But if they're in order and it's a data structure where you have random access, you can do a binary search. So sorting inherently gives a data structure more information. Okay? And we use sorting all the time. Don't we use alphabetical lists? Don't we use sorted lists of this and that, and for class descriptions, right? If you're looking up a class, it's numbered. That's a sort. Things get sorted all the time. Okay? So we need to talk about this in terms of data structures because it's important to know how to do sorts, and it's also important to kind of understand the idea of there are lots of different sorts, so let's pick the right one for the job. Okay? So sorting is simply this. Put elements in some order, right? And that order is generally something we're used to, like alphabetical order or numerical order. Okay? You can actually make it any order you define as long as you define it properly. And that's based on whatever you want. As long as you define the order such that you know when it's in order, then we can do a sort on that. Okay? All right. Sorting, I love this definition of sorting. In order for a list to be sorted, it must be in non-decreasing order, which it could also be what? Not non-increasing. Increasing. So you'd think it would be increasing, right? 1, 2, 3, 4 is increasing and also non-decreasing, correct? Yeah, if you have 1, 1, 2, 3, 4, that's not increasing because 1, 1 is not increasing. It's non-decreasing, but it's not increasing. So that's where that definition comes from. That's all this means. It means that you can have duplicates in your list. Okay, we'll talk about the specifics of if duplicates matter when you're doing sorting. Sometimes they very much matter. Okay, it also has to be a permutation of the input. So remember back to either discrete math or any kind of combinatorics class you took, but a permutation is just rearrangement of the same things that you've started with. That's all that is. Okay, and then if you do that, if you make your list in non-decreasing order and it's just a permutation of what you started with, it is now sorted. Fair enough? Okay. All right. Sorting is not a new topic, right? I mean, sorting has been around since, in math, people talk about sorting. In computer science, it's been around since like the very beginning of computer science. People needed to sort things, so they figured out these algorithms how to do it. We're talking like the 40s, 50s, 60s type 1940s, 50s, and 60s time frame, right? But people are still coming up with new and interesting sorting algorithms. There was this guy named Tim who created a sort called Tim Sort, because why not, right? In 2002. So that's not too recent. I mean, what, 12 years ago, but more or less fairly recent in terms of algorithmic development. Anybody ever used Python? Python programming language? Yeah, the sort that you use in Python to sort things that's built into Python is a Tim sort. Because the Python people said, hey, wait a minute, that's a pretty good sort. We're going to use it. Right? And so they did it. It actually beats out a lot of the other sorts that they could have chosen from. So kind of neat. Still somewhat active research. Okay? So to get to the, to kind of, what's the word? To kind of give up the end result here of all of our complexity stuff, the best you're ever going to get for comparison sorts, and we'll talk about there's some other types of sorts. For comparison sorts, you are never going to get better than order n log n by doing a comparison sort. Okay, that's provably true. When you take algorithms class 160, you will talk about why that's the case. But it's provably the case that if you have a comparison sort, which means basically take two numbers and look at what their order should be and swap if necessary, that's a comparison sort. Those kind of sorts can't do better than n log n. Okay? Is this better than linear or worse than linear? It's worse than linear, okay, because it's n times log n. So it's actually worse than linear, which means that sorting in general is not a fast operation. Okay? Is it better or worse than log n? Also worse, because it's already going to be worse, right? But so again, sorting is not a particularly great algorithm. Is it better or worse than n squared? Better than n squared. So it's kind of in the middle there. All right? So this is what we're going to strive for with all these algorithms. We may not get there, but we're going to strive for it because that's the best you can do. Okay? So if we see an n log n algorithm for a comparison sort, we're going to be happy with it because we're not going to be able to do much better. In fact, we're not going to be able to do any better for a comparison sort. Okay? That's the time complexity. We also have to think about this other interesting idea called the space complexity. Okay? What that means is, let's say you have an array. Let's say you have an array like this, right? And it's 4, 1, 3, 2, right? And you want to go and sort that. Okay? If you did it like this, let's say you found a sort and you had another array, right? And you said, let's find the minimum one, and put it here. Let's find the next minimum, 2, and put it here. Let's find the next minimum, 3, and put it here. Let's find the next minimum, 4, and put it there. That has a space complexity of, what do you think? If there's n here, how many are here? Also n, so the space complexity, it's actually 2n, because we've had to do double the amount of space to store the the sorted part versus the original. Okay? Many times, in fact, today we'll talk in particular about 4 different sorts that are all what we call in place. Okay? Meaning that instead of duplicating the list, right? We're just going to say, OK, let's find the one that needs to go and then figure out where it can be swapped with or whatever, and then do the same thing for the next one. Notice that I'm not using any extra space, right? And then, whoops, I did it wrong anyway. 2, 4, 3, and then 3, 4. OK, notice that I started with n elements and there's no extra space needed. That's called in place. OK? Now, you can generally have an extra element, and it would be like n plus 1, but we still consider that n complexity. Like if you have an extra one that you're storing temporarily, that's not really, we don't worry about that extra 1 or 2. OK? So we have to worry about space complexity and time complexity. OK? Questions? Not too bad. OK? The other thing about in-place sorting, this actually goes back to the duplicates we talked about. 1, 1, 2, 3, 4. OK? If you have a stable sort, actually this is not the best example here. Let's do it this way. 1, 1, or 1, 2, 1, 4, 3. If we're trying to sort those numbers, and we do a stable sort, that means that this one, we'll call it x, versus this one, we'll call it y. They have to end up in the same position at the end. 1, 1, 2, 3, 4. Right? And this one's going to be the x one, and this is going to be the y one. Now, for integers, it doesn't matter, because you can't tell the difference between a 1 and a 1. But let's say these were keys, and you had some sort of data associated with it. A stable sort says, OK, this one comes before this one in the original. It has to come before this one in the sorted list. Does that make sense? OK? The stable sort says, OK, we're still going to sort these, but you can't disrupt the order of the actual elements, even the duplicates, or especially, in particular, the duplicates. OK? All right. So we're going to talk about sorts for two lectures. That's how kind of big this topic is. There are a ton of good websites that deal with sorts. Okay, I'm going to show them to you right now, a couple of them anyway. There's this one, which is my favorite website on sorts. OK? What this does is this actually, you can see across the top, it lists a whole bunch of different sorts. In fact, we're going to talk about all of these except quick 3. All right, although you're perfectly welcome to implement quick 3 for your homework assignment. We're going to talk about all these other ones. And then down the side, it actually puts like different ways of arranging a set of numbers. And what's cool about this is they do it with these bars. The smaller bar is a smaller number. A larger bar is a larger number. And what they want is this to be in order. OK, so for instance, the reversed one, they want it to be the other way when it gets sorted. OK, so what's really cool about this is if you click on the little, or the big button up here, it will sort everybody. OK, and you can see which sorts are better than other sorts. OK, in fact, the selection sort is one of the ones we're going to learn about. That's a terrible sort. The other one, but we'll learn about it, and you'll have to program that one. And then the other one that's a terrible sort is, well, I will, as David said, I will let President Obama tell you about this. Let's see. Obama, Google sort. I think that's what it is. Yeah, here we go. So President Obama, as David said, was at a, hello, there we go. President Obama was at Google for an interview before he became president, so like a Senator Obama. And they asked him some questions. How many people have seen this one? A few people? OK, well, I'll let him tell you this.
get a job as president, and you're going through the interviews now. It's also hard to get a job at Google. We have questions, and we asked our candidates a question, and this one is from Larry Schwimmer. What, you guys think I'm kidding? It's right here. What is the most efficient way to sort a million 32-bit integers?
Well,
I'm sorry, maybe.
No. I think
it's not
I think the bubble sort would be the wrong way to go.
Come on, who told us this? I didn't see computer science.
We've got our spies in there.
Yeah. Why not? Let's ask a different interview question.
So President Obama says bubble sorts are terrible, and so you should never program a bubble sort. So don't do it. I don't care if they teach it to you in ES3 or whatever class they teach it to you in. You should not do a bubble. We're not going to learn about bubble sorts. We're not going to do them. You're not going to be allowed to do them for your homework. But skip that one. Okay. But other sorts. What's interesting about this website is that you can also say, hey, look, let's look at the insertion sort itself and just compare the insertion sort. Well, let's do a different one. Let's do quick sort, which is an interesting one. We'll talk about quick sort in the next couple of days, right? You might not be able to tell exactly what's going on because you don't understand it yet, but that's OK. Notice the one that takes the longest time is down here. This is an interesting set of numbers. Notice that there's like only 4 groups of numbers. So there's only a few unique different numbers in that set. That's what it is. And it turns out quick sort, which is one of the sorts, happens to be not so good when you have a few unique types of numbers. So it's interesting. We have to talk about those things. Like when does it make sense to use one sort over the other? Okay, well, if you already know something about your data set, that's fine. Some algorithms are great when it's nearly sorted. Let's see which ones finish first when it's nearly sorted. Insertion's done, right? And the other ones are just selection sort, just keeps on going, right? Okay. All right. So that's one of the good web pages. Another one is this one, which is the same web page I've showed you a number of times, but this one it allows you to do the same thing as we've done before. You can actually I'll go a little faster, but you can do sort. So let's do a quick sort on this one, right? What it does is it does the algorithm kind of for you here, right? And it shows you how it's doing it. Okay. In fact, I'll speed it up and let it go a little faster. And again, if you don't understand this, you've never seen it before, that's cool. But in fact, it's the numbers are over there. You just can't see them anymore. They've just kind of, the highlighting's not so good. But in fact, it's almost done with this sort, as it turns out. Well, getting there. Almost done. And there we go. Now it's sorted. So you can see it in here, and you can slow it down and speed it up. So if you get a little confused about the algorithms we're talking about, go to one of these web pages, click on the little buttons, and you can watch these things happen. So visualizing this stuff is pretty cool. And if you're not a visual person and you actually like, you're more of an audio person, this is one of that's loud. Oh, sorry. This one will make your ears bleed a little bit. But what this one is a visualization with audio as well of a whole bunch of different sorts. In fact, it's called 6 sorts or what was it called? So many sorts in 6 minutes. It's 15 sorts in 6 minutes. So I think we've got 6 minutes. We can watch this. I'll try to make the volume tolerable, but let's see. Yeah. Hold on. What it's doing is it's the audio part. Whenever it touches one number, it actually plays a little tone based on how big the number is. The tiny little ones are like really low pitched. The really like tall numbers are really high pitched. And so that's what it's doing whenever it's touching this. And you'd be surprised that like if you watch this a few times and like close your eyes, you can actually tell which sort it's doing based on the sound. And it's fun. Okay, this one is insertion sort, which we're going to talk about in a few minutes. Also not the best sort in the world. Yeah. Hurry up already. There we go. Okay. The next one, quick sort. Right. So quick sorts, when we talk about it, you'll think it's a pretty cool algorithm. Kind of breaks into smaller pieces, yeah. There you go. Okay. This is merge sort, which we'll learn about. This one is, once you see it, you'll go, oh, look what's going on, right? Right? That was a cool one. This is heap sort. Remember this. Remember this when we do heap sort in a few minutes. You'll see what that's talking about. Right. Okay. This is a really cool sort. This is called Radix Sort, which we're going to talk about next week. It's another very unique sort. This is the other. This is Radix Sort, except the other Radix. You'll see what I mean when next week. This one's, yeah, a little bit like quicksort. Okay, then it does some of the standard sorts from the library, from the standard C library. This is a non-stable sort. The next one that does is actually a stable sort, which I bet you'll recognize. This is interesting too. This part right here, notice what it's doing. Small little chunks. We'll talk about that too. This is the stable version of the same sort, meaning it has to keep them in order. What kind of sort is it doing? It's a merge sort. Oh. The unstable doesn't have to keep the duplicates in the same order. Yep. Okay, let's see what's next. Shell sort. We'll talk about this one in a few minutes, at the end of class actually. Notice these guys are getting closer together. Talk about that. Now they're really close together. And they're extra close together. Okay. Notice how many fewer elements we have here, by the way. What's that? Yeah, because this needs to be doable. Cocktail shaker. Right? Yeah.
So it's like bubble sort, except slightly not as
Yeah. Yeah. I don't know why this is called the gnome sort, but maybe it looks like a gnome from the side or something. I don't know. Bitonic sort. This is like a, it basically goes in two different directions at once sort of thing, and yeah, it's weird. We won't learn about this one. You can try to program it though. Not bad. So This one's called Bago sort. Now, I will not let it continue. It's kind of fun. Well, look, hold on. All right. There's 20 seconds left of the whole video. Yeah. So, yeah. So Max, why didn't it finish Bago sort?
It's just randomly moving elements until maybe it's sorted once.
Yeah. So Bago sort is what we call a stupid sort, where it basically says, and I think this is the right algorithm: is it sorted? If not, shuffle it all. Is it sorted? Shuffle it. Is it sorted? Right? That's what it does the whole time. So, not a good sort, right? Yeah. So go back and look at some of those. They're kind of fun. Once we learn about them, if you watch it again, you'll go, oh, I get that now. I see what's going on here. It's in some cases. Some are a little hard, but some of them you can see what's going on. OK, let's start learning some details about these sorts. The insertion sort. We have already talked a little bit about insertion sorts. OK, we did an insertion sort when we looked at the priority queue list. OK, we did an insertion sort. And what we did was if we had 4, 1, 2, 3, 7, right? If we did 4, 1, 2, 3, 7, what did we do to do the insertion sort? Do you remember? Like, how do you put 4 in an array? Where do you put it? Right at the beginning. OK, and then you put 1 in there. How do you find where 1 needs to go? Yeah, you actually go backwards, and you go, OK, is 1 less than 4? We're going to do it from the smaller one over here. It is. So 4 needs to shift over. You put 1 there. How about 2? Yeah, same thing. It shifts. 4 needs to shift over, and you put 2 there. How about 3? Right? Same thing. This is not a good example. Let's see. We'll do 0. Right? 3, and then we'll put 7 in there. And where did 4 go? 4 and then 7. And then if we put 0 in, 7 has to go here, 4 has to go here, 3 has to go here, 2 has to go there, 1 has to go there, and then we put 0 in over like where that is. Right? Everybody shifted over. That's an insertion sort that's done when you have a list of numbers that you're putting into another array. Okay, it is not in place because we had to somewhere store these, and then we're putting them into here. There is a way to do an in-place insertion sort. Okay, you can actually do an in-place insertion sort. Here's the algorithm. Let's say you had the following numbers. Okay, you iterate through the list, starting at the second one. Why? Because the first one doesn't need to compare to anybody, right? So you start at the second one, and you compare it to the one before it. And if that one needs to move over, you put it in the place where the one you're comparing is. And you kind of keep the one that you're comparing as a temporary. Okay, and then you just keep going down the list, boom, 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 until you get to the end, shifting everybody over 1 until you get to the end. That makes sense? Okay, so let's look at this. In this case, we're going to start with the 5 and compare it to the 9. Is the 9 going to have to move to the left or to the right? Yeah. So we take the 5 out, we move the 9 to the right, and we end up doing that. And then we take the 10. Does the 10 need to do anything? No. Right? 10 needs to stay right there. How about the 8? 8 needs to go 2 over, so 10 needs to come this way, and then 9 needs to shift this way. Okay? 12 doesn't need to change. 11 needs to swap with 12. Right? 14 doesn't need to do anything. How about 2? 2 is ugly, right? Because 14 needs to go, then 12, then 11, then 10, then 9, then 8, then 5, and then you stick 2 all the way at the end. Not so fun, right? Boom. OK? And then 22 stays where it is, and 43 actually stays where it is. Whoops. There we go. OK. I didn't want to give away the answer. What's the algorithmic complexity of this sort? Worst case, let's say. I heard it. Think about it for a sec. Let's let everybody else think about it for a sec. Worst case for this. What did you say? I think n squared is right. Can you give me an ordering where it's going to be n squared most of the time? Yeah, what if this was a reversed list, right? If it was a totally reversed list where it was 2, 5, 8, 9, 5, 8, 9, what do we have next? 10, 11, right? Well, what you'd have to do is you'd have to swap 10 with this one. Then you'd have to go to the 9, and you have to go boom 2 over. So these have to shift 2. Then you have to do 8, and those have to shift over in there. It's not absolutely n squared, but it's on the order of n squared, right? Which means that basically you're going to have to go through, for every element, you basically have to go through the list the whole time, or the whole way. Not quite the whole way, but it's enough that it becomes n squared. What's the best case for this sort? Best case for this sort. If it's already sorted, take a look at this. If it's already sorted, we go to the 5. Do we need to do anything? Nope, 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 nope. How many times did it go through? 1. Just once through n times through the list. So you, or n time through n numbers in the list, and you don't have to do it. So the best case and worst case are there. Average case is actually, as it turns out, n squared as well. How do you figure out the average case? Well, we got to talk. I'm not going to make you guys figure out average cases. Okay? In fact, I don't even think I can figure out the average case for a lot of these things because the math gets really hairy really fast. There are papers written about this stuff. You can go to Wikipedia and it will tell you the averages. And if you want to dig deeper and figure out why, you can do so. When you get to algorithms class, you might go into some of the details about that. Okay? What's nice about the insertion sort, even though it's a terrible sort from the standpoint of worst case complexity is n squared, on average, it's n squared as well, but actually for small arrays, I'm using the quotes here for a reason, for small arrays, it's actually pretty fast, right? Because smallness doesn't matter if things are n squared. What do I mean by small? 10 to 15, right? I mean, it's kind of empirical. It doesn't really, you don't really get the, you can call small 10 or 50. It doesn't really matter. But generally, other sorts will sometimes use an insertion sort for when they get to a section where they have tiny little pieces they need to continue to sort. Why do they do that? Because this is low overhead. In fact, almost no overhead. It's like a for loop, right? Or I guess a double for loop, but it's easy. Okay? Not even a double. I guess one for loop. It's pretty easy. And you can, no, 2 for loops, I guess. But it's easy. And you can use this for a small one. Remember the sort in the one that made your ears bleed, where I said, hey, look at the little pieces, and it was doing a totally different kind of sort? That's what was happening here. It was doing an insertion sort on the tiny little pieces. So that's nice. Okay? Questions on insertion sort? You will have, this is one of the sorts that you might want to do for your homework. You don't have to, you could. Okay? All right, let's talk about selection sort. This is another terrible sort. Tell you that up front. Okay, it's a terrible sort. What it does is it basically says, here's your list. Where's the smallest element? Swap that with the leftmost unsorted element. Okay, and repeat. Easy. It's a very easy sort, right? Let's see. I want to do it this a couple different ways, actually. I want to show you this one in 2 pages. Oops. There we go. I want to show you this in 2 pages. You'll see why in a minute. There we go. Well, we'll do it here. OK. Watch what comparison sort does. OK, I'll even make this fast. Oh, it doesn't have it here, does it? No, selection sort, rather. There we go. OK, watch what it's doing. Going through and let me slow it down a little. Well, that's probably too much. OK, it's going through and it's figuring out where the smallest one is, and it marks the smallest one in pink, right? And then it says, OK, go back, mark the smallest. So that's the smallest one. The next, it's going to get to here, and that one's going to be smaller than the one that's, no, it's not. This one maybe will be smaller, and it will then make that one pink, and then et cetera, and then it does that. Why is this slow? Because it has to go through the whole thing for every single number. Okay? Which means, what's the asymptotic complexity? It's n squared. That's the worst case. What's the best case asymptotic complexity? How do you make, OK, what order would you have to make it n? OK, if it's already in order, let's say it's already in order. 1, 2, 3, 4, 5. OK, selection sort says, go through and find the minimum. Minimum Here's the minimum. It's put it in order. Minimum. Here's the minimum. Put it there. Minimum. Right? It's dumb. It's a terrible sort. But the point is, it is always n squared, no matter what. Right? Like, it's not a good sort because of that. In fact, you can see that, and this is why I wanted to keep it here. Remember how we sorted this one before? If I now apply the selection sort to this one, right? Oh no. It has to go through the whole thing. Even though it's already sorted, it's saying, well, I'm just going to do my thing, right? And go through it all the way. So that's not too fun. OK? All right. Here's how it works in practice, right? You say it's particularly slow. So you say, OK, look, find the minimum. The minimum is 2. OK, find the minimum. The minimum is 5. And doing that, you have to go through the whole list. No way around it, right? 8, etc. OK? Easy. This is one of the ones you will have to do for homework. This is such an easy one. You will like knock it out of the park. OK? Easy sort to do. OK? Worst case, best case, average case, everything case, right? The only thing it's good at is it's an in-place sort. It's about the only time you'd ever want to use this. No, you'd really never want to use this. Like for real. Kind of like bubble sort. OK? Kind of like bubble sort. OK. The next one is heap sort. So we actually kind of talked about heap sort a little bit. OK? We talked about heap sort a little bit. We didn't necessarily talk about doing it in place, though. OK? Let's think about this. If we're going to do a heap sort, we need a heap, first of all. OK? So let's make a heap. I should have done this in a max heap, but we're going to do a min heap, and the order will be backwards. Don't worry about it. It's just backwards. You could do it with a max heap. But let's stick to what we already know. 2, 10, 7, 15, and that's good. OK? Where is the, well, question. What was our algorithm for, well, it started out right up here. What's the algorithm to do a heap sort? What did we say? We always know something about a heap. What do we know? We know the parents are higher, but what do we know about the root? It's the minimum, right? So if we want to find a heap sort, we remove min, right? Remove min, and then we're going to rebubble. We're going to put the 15 here, bubble it down. 7 will end up as the root. Then we pick the min off, 7. We replace it with, in this case, it would be 10. 10 will bubble. We'll actually go up here, bubble. Let's see. Sorry, it would be 2. 7, right. It would be 10. 10 would stay where it is. 15 is going to be bumped up 1. And then it's going to be 10 and 15. And all you do is you remove. That's all you have to do. Remove min multiple times until you get to the end of the heap. Can we do it in place? Right? I mean, it says so, but without looking at the board, can you think about how we might do a heap sort in place? Question. When we do a remove min on the heap, which element is gone afterwards? Let me add one more. Let me add 12 here. Which element is gone after we do a remove min? The 12 is now going to be pushed up here somewhere, 12, and then it bubbles down, and this is going to be gone now, right? Why can't we just keep the number we just removed here, right? And just know that the heap does not include this one anymore. Because our heap size started out as 1, 2, 3, 4, 5. Once we do a remove min, this one will now be gone from the heap. And how many elements are left? 4. So this is the last one in the heap. So when we do bubbling this down, OK, here's what I'll do. I'll just make this one like blocked out. It's there, but it's not part of the heap anymore. 12 bubbles down. 12 gets replaced with its minimum child, 12. The next remove heap we do is 7 goes away. We're going to replace it with 15. Whoops, 15. So let's just keep the 7 there, and this one's no longer part of the heap. But now it's there, right? Same thing. The 15 bubbles down. It's going to bubble down to here. 10 is there. Oops. Okay, 10 gets removed. Which one does it replace? The 12, because it's the next one that's in the heap, right? So the 12 goes here, 10 is here, and this is no longer part of the heap. It doesn't need to bubble down. 12 goes out, right? And 12 goes here, and 15. And now guess what? We now have it in order, backwards, 15, 12, 10, 7, 5. That's how a heap sort works. Okay? I'll show it to you. If that was confusing, I'll show it to you. Okay? It's actually just backwards, like I said. OK, you have a bunch of random numbers in your array. First thing you do, heapify it. We know how to heapify it, right? We go to the, and if you forgot this from the other day, go remember it, right? We go to the one with the farthest one that has, the first one that has, what was it again? The last one that has children. I think that's it. We go to the last one, heap size divided by 2. We go to the last one that has children, right? And we down heap it. And then we go to the next one, we down heap, et cetera, et cetera. And then in the end, we will end up with a heap. Right? That's the way we ended up getting our heap, doing heapify. Now that we have the heap, we do this remove, replace business, bubble down, as follows. OK, we've got a heap. We do a remove min, which takes the 2 off. And we take the last one and we replace it. So we basically swap those two, right? And then bubble down the 43. Unfortunately, 43 is big, so it needs to bubble all the way down, right? 43 bubbles all the way down. OK? Then we take the next min, which is 5, right? And we replace that with the min. We swap those two again. And we bubble the 22 down. It means the 22 is going to go this way, then this way, right? Like that. Okay. Swap the 8 with the 43. 43 gets double duty in this one, right? 43 has to go there, and 43 has to bubble down. Doesn't have to go quite as far, right? And then the, let's see, the 9 and the 14 get swapped, and 14 bubbles down, et cetera, et cetera. OK, do you see how that works? If I gave you a pop quiz, could you repeat it? Some people are like, no. All you're doing is a remove min on the heap. And you're just saying, where do I need to put it? In the empty spot that I've removed from. Right? That's all there is to it. OK? It's algorithmically speaking, OK? It's actually pretty good. It's our first n log n performance. Worst performance is n log n, best performance is n log n, average performance is n log n. This is not a bad sort. OK, it's not a bad sort at all, because we already said that n log n is the best we can do. It happens to have more constants in here than some of the other sorts, so it's not used that often. But it's a pretty darn good one. It's easy to do. It's in place. It's a pretty good sort. OK, heap sort. You will practice this heap sort on the lab next week. OK, you'll practice heap sort in the lab, which is one of the reasons you can't do a heap sort for your homework assignment. Ah, too bad. OK. All right. Do we need a break? Do we need like everybody stand up and wave their hands because we're tired? Yeah? Take a 2-minute break. Stretch out. We're going to go to shell sort next, which takes some brain power. 2 minutes. Be back. All right. Are we shaking out now? We can make it through the rest of the 20 minutes? OK. Maybe we'll do that more often. Instead of me finishing 2 minutes early when you guys are like asleep, we'll just shake it out for a couple minutes. All right. The next sort we're going to talk about is this thing called a shell sort. Now, when I actually first heard about this sort, I didn't know about the details about it. I learned about the algorithm, but I didn't know any details about the creator and so forth. But I thought it had to do with, you ever seen that shell game where you're moving shells back and forth, right? I kind of, for whatever reason in my brain, I thought, oh, that's what this is, must be related to something like that, shells and putting things in whatever. No, the guy who invented it was named Donald Shell. So that's why it's called the shell sort, because he invented it. It's like Tim, I guess. This is a very interesting generalization, although that might not be the right word, specialization, I suppose, of insertion sort. Okay? It uses insertion sort as its algorithm in a very special way. Okay? Let me read through the algorithm, then I will show it to you, and I think all things will be made more or less clear. Okay? What you do is you take the elements, okay, and you basically perform an insertion sort on a certain arrangement of elements that are a number of places apart, a fixed number of places apart. Okay, I'll draw it for you in a minute. Okay, so basically we rearrange the elements so that looking at every hth, that's a terrible one to do, I should have used h, but hth element, okay, produces a sorted list, which is what we call h-sorted. I will show you what that means in a second. Then you change that number that you've used to a smaller number, and we'll talk about how those numbers get picked in a second. And you do it again, and you keep doing that until the number of the gap is 1. This is what I mean. Okay? So let me show you how this actually works. Let's say we had an array that looked like, I'll make it a little bigger. Let's say that we had an array that looked like this. Okay, and we put some numbers in it, 7, 2, 4, 9, 1. By the way, humans are terrible at randomizing a number of, picking out random numbers out of your brain. Brains are just terrible at that, right? Computers are much better. In fact, when I was a freshman in college, I took an engineering class, and the professor asked us he took half the class, and he split us in half. And he said, this half, I want you to go home and take a penny and flip it 100 times and write down the heads or tails and come in the next day and hand it in. And the other half of the class had to go home and make up runs of heads, tails, heads, tails, 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 heads, whatever, right? And he handed those in. And he got up to the front of the room, and he said, don't tell me which group you're in. Right? He got up to the front, and he handed them in, and then he started going through them, and he said, so-and-so, you flipped coins. You didn't pick it out of your head. And the guy, yeah. And then he got to me, and I had done it on I had made it up. And he goes, you made it up. I go, OK. And he went through, and he got every one of the 25 of us in class right. Right? And we're like, holy cow, how'd you do that? Anybody have any ideas? Yeah.
We did it in finance class.
And?
So, we simply don't believe in, if we think that we can't get 6 or 8 tails, in a row, that's why it's just we keep changing it.
Yeah, you can't get that many in a row. It turns out that when you really flip coins, it's very realistic to get 6 or 7 or 8 heads or tails in a row. And nobody ever thinks to do that when they're just making up numbers. They'll never do heads, 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 right? 7 times, exactly. So that's how I figured out. But anyway, my point was I'm terrible at picking numbers out of here. 15, 3, 6, 11, and 12. OK, so you've got this set of numbers. OK, 0, 1, 2, 3, 4. Actually, I believe for whatever reason I did it starting at 1, probably because I did it with a heap sort that way. 5, 6, 7, 8, 9. Let's say we had this arrangement. What we mean by doing and having something h-sorted, let's say our size was 5. OK, our gap was 5. This one, and then 3, 9, 10, 11. And this one would all be sorted relative to each other. OK? So forget about all the other numbers. We have to sort the 2, the 3, and the 9. They happen to be already sorted, right? In this case. The other thing we have to do that for all the different gaps of that size. So in other words, the 4 and this one, and there's no more there. And then this one, and this one, and there's no more there. And right, this one and this one. You get the idea? The first thing we do is we sort the 2 versus the 3 versus the 9. Then we sort the 4 versus the 6. And then we sort the 9 versus the 11, et cetera. And so what you end up with after one round of this is a partially, in some sense, partially sorted list where it's sorted by a gap size of 5. OK? Yeah, John?
So when you're doing those gap sorts, how are you sorting each one?
You're doing an insertion sort on them, actually. Yeah, so you just do the insertion sort. This is a good one to try for your homework. It's a little tricky, only because you have to figure out how do you do the gaps. You can do it with for loops. It's actually pretty simple, but you have to figure out the gaps. But the bigger question is how do you pick the gaps? But we'll get to that in a second. Then you do a smaller gap. So this was the 5 one. Then if we want to do a 3 gap, right, we would then resort this one, 1, 2, 3, this one, 1, 2, 3, this one, 1, 2, 3, this one, and then this one, and this one, and this one, and this one, and then we would do this one, and this one, and this. You see what I mean? And that, now we resort those as a its own like gap sort. And then you go down to 1, and that sorts the rest of them. Now, the big question is, why is this actually better than insertion sort? This is an interesting question. What did we say insertions? When did we say insertion sorts were good? For small lists, and also for lists that are also what? Mostly sorted, right? So what we're kind of doing is we're chunking this up to some extent. If this is like a random list of numbers, right? We're kind of saying, okay, it's already random. Let's chunk it a little bit and say, now we're going to go through, do an insertion sort on part of it, and then it's going to be more sorted than before as a whole. Then you're going to do it for a smaller chunk, and it's going to be more sorted than before. Every time it becomes more and more sorted, insertion sort starts to work a little better, right? So that's kind of neat, okay? Let's do this, then I'll talk more about the gaps themselves. We're going to do a shell sort on these numbers with 3 gap sizes. You always have to end with a gap size of 1. We're going to start with 5, then we're going to do 3, then we're going to do 1. I've tried to color code this so that it makes sense. It still gets a little like crazy when you try to look at it all in one piece, but we'll see if we can make it through. This is the original list. Okay, I'm starting on 1, I think because I did heap sort that way, but anyway, I've color coded the gap size of 5. Okay, so the red numbers are a gap size of 5, the yellow numbers are a gap size of 5, etc. Okay, see how that works? That's the gap sizes. What we're going to do is we're going to sort those ones by themselves. So watch the next slide here shows this. Okay, the original was up here. This is now the sorted one down here. So the red ones, which were 62, 17, and 25, have now been sorted in their own group. 17, 25, 62, right? And then the yellow ones were sorted. It was 83, 53, 90, or sorry, 83, 95, 28, 28, 83, 95. Those are sorted. So you see how that works? It's done it now by gaps. So we did that for the whole thing. Now we're going to do a gap size of 3. Okay? The gap size of 3 ends up, well, I've done down here, I've showed you that. Now it's going to be this one, this one, this one, and this one, and this one, this one, this one, etc. Okay? And so now when we do that, well, again, it looks a little crazy, but it started out with the red one, 17, 47, 83, 69. 17, 47, 69, 83. So those are now sorted. Okay? 28, 7, 86, 62. 7, 28, 62, 86. Okay? So see how those are now sorted in their little groups? We have to do one more sort. But what's nice about this one? In the big picture, it's almost sorted already. Right? And when you think about it, it's more or less sorted. Like there's not that much more that needs to be sorted, right? I mean, 7's way down here, 95's way up here. You've got like more or less pretty good sort going right now. Yeah?
It's like the smallest of a group of 5 is next to the smallest of the other groups.
Yeah, and the way you pick the gaps is rearranges inside, like you have to redo it, but yeah. And it goes to 3 and it resorts those. And so this is almost sorted. So when we do an insertion sort on this, it's pretty fast, because you don't have as much sorting to do. So it gets faster and faster and faster. Okay, you end up doing the 1 sort, and this comes out. The gap sizes is the part that's interesting, right? If you go to Wikipedia and you search for shell sort, this comes up like it's the shell sort algorithm, right? And it shows you the shell sort. And down, they walk through one. And then they say, here's some gap sizes. Okay? It's hard to see from back there, but people have written research papers about these things, right? If you pick a gap size that's n divided by 2 to the k for some k, for an example, you get n divided by 2, n divided by 4, all the way down to 1. This has an asymptotic complexity of n squared. Not so great, right? But if you go and you pick, let's say, well, 2 to the k minus 1, so this is backwards. Let's say you did 63, 31, 15, 7, 3, 1. N to the 3 halves, which is better than n squared, right? Not significantly, but better than n squared, etc. And these are all you can look up some of these papers right here, right? Anybody ever heard of a guy named Donald Knuth? Yeah, he's one of the most famous computer scientists ever. worked on this problem, right? Okay, and you go down here now. Here's some really interesting ones. Look at this. Question mark for the complexity. Question mark, question mark. These are still unsolved problems. Okay, so there are still like unsolved problems in sorting for shell sort. We have no idea what the asymptotic complexity on average is for shell sort. Right? We can find the worst case. Average, you're like, I don't know. Right? You could probably do something empirically, but it's tricky. Yeah? So, that's a good, no, I think somebody picked this and then tested it, I guess. And then this one seems to be kind of fast. I mean, I think that's maybe what it is. I don't know. Or maybe they just didn't know it for the Wikipedia page. That might be it. But yeah, you can do that. But anyway, point is, even some sorting algorithms, we don't know the average or even worst case complexity for some of these things. So shell sort's one of them. Okay. All right, let's see. So that's there. The complexity of a shell sort in general, the complexity is n squared. So it's not so great. Right? Best performance, I didn't see any n log n's on there, but maybe there's a best performance in n. Oh, I guess you could have it sorted such that there's an n log n. Okay? And average sort, who knows? It is definitely in place, though. Definitely in place. Okay? Questions on shell sort? This is a good one when we're talking about for your homework assignment. If you want a tricky one, that's one of the ones that it's not too hard. It's just a bunch of insertion sorts. Pick that one. Okay? All right, we'll do that in a second. What I want to talk about here is homework 5. So later this evening, I'm going to post homework 5. It will be due, what did I say, 2 weeks from Friday? Or week and a half, 2 weeks, I guess. A little over 2 weeks from now. That's plenty of time to do this, trust me. Okay, as long as you start relatively early, giving you the evil eye. You have to write 3 sorting algorithms. Your first sorting algorithm has to be selection sort. It is so dead easy, you could do it like in 2 minutes. Okay, it's really easy sort. The second sort can be from the following list: shell sort, merge sort, quick sort, which we haven't talked about yet. We talked about shell sort. Merge sort we'll talk about Monday. Quick sort we'll talk about Monday. Insertion sort, also pretty easy, all things considered. Okay, and you can pick one of those. You have to pick one of those. Okay, if you want an easy one, pick the insertion sort because it's pretty easy. All right, this is like your chance to like have either a fairly easy assignment or like go and do something kind of cool and do like a harder part of the assignment. You can't implement bubble sort or heap sort. I told you already about bubble sort. Heap sort you can't do because it's part of the lab next week, so I'm not going to let you do that one. And then you can choose a third sort also from the list, or any other sort that's not a stupid sort like Baga sort. Okay? I know, sorry. Well, you can't be, well, first of all, you could, but then it would fail all the tests because we're timing them. So, okay? So you can choose a third one, but you can't choose like the stupid sorts. Yes? You can try to come up with your own. We had people, you totally try. Yeah, we had people in last year's class come up with their own. A number of people tried it and ended up saying, oh, if I make this change, it'll be better, and if I make this change, and then all of a sudden they ended up on merge sort. Right? So they like tried to come up with it and then realized that there's a reason we talk about all these. Right? Because they tend to be like, if you think about you, but you are totally welcome to come up with a new TIM sort, right? Okay, so you come up with a max sort. Hey, maybe it'll be in Python 7 or something. Who knows? Python 4. But that's the assignment, okay? Couple caveats about this assignment. You have to write basically 3 main files, main CPP, like selection sort, main1.cpp, main2.cpp, main3.cpp. If you use the make file, it will know how to compile everything. If you try to do it in Eclipse, it will freak out when it sees 3 different main files. So what you can do while you're testing one in Eclipse is change the name of main1 to main1.tmp or something like that, and it won't try to compile it. That's all you have to do there. It's not hard. Just if you run into trouble, let me know. You have to do most of this on your own. Like I give you a very, very rough skeleton here. Okay, so your job is to go and actually, for once, like write the whole program for 2 of the sorts. Okay, so that could be a little bit tricky. Not hard, but you have to do that. And obviously, there's the 3 things here, but you get to pick which ones you want. Finally, this homework is going to be graded in person which means you're going to submit it. There won't be many provide tests. Like basically it's going to say, OK, it looks like you can sort them OK. Right? But that's about it. Like it doesn't have to do anything else except sort them. So there's not going to be a huge suite of tests. But what we will do is we will run our own tests that test for how fast your algorithms go for various types of input. Like we're going to try the input reversed. We're going to try almost sorted. We're going to try every other one is like small, big, small, big, small, big. And we're going to test it. And you've got basically 3 minutes to pass each test. But your grade is not necessarily going to be based just on that. It's going to be based on you coming in and saying, explaining the results. So you're going to come in and you're going to say, hey, this one took this much time. Why did it take this much time? And you're going to have to say, oh, because it's an n-squared algorithm and this makes sense. And then we're going to say, what if you had this many elements? And you'd say, oh, it takes this amount of time. Right? I'm being vague about that because you have to figure that out. But that's going to be part of your grade. Does that make sense? It's going to be in person. Basically, you sign up with your 2 TAs, or me, and we sit down with you, and we talk through your program, and we talk through your programs, and we talk through the actual results. OK? It's kind of a cool way. I think it's an interesting way of grading. And people seem to enjoy it. The TAs don't love it because it's a lot of grading. There's a lot of time. Because you each get like 20 minutes. But that's about it. OK? And some people take 5. I mean, it's not like if you know what you're talking about, you can get out of there in 5 or 10 minutes. But some people take 20 because they're like, I don't know what's going on. So that's that. Questions on the homework? I'll post it after I get back to my office. OK, last thing I want to show you. Who took Comp 11 in here? You've probably seen something exactly like what I'm about to show you. Probably not this one. But this is shell sort as interpreted by a bunch of Hungarian dancers. They did a whole bunch of, you watched like Selection Sort or something in the other, yeah, right? So what they're doing is they're doing a gap size of what, 5? 6 maybe? Right? And if they need to swap, they do, because they're doing an insertion sort as part of their sort. I kind of want to learn how to do Hungarian dance now, actually. Anybody from Hungary? Nobody from Hungary?
Yes.
Right. Now they're doing a gap size of 3. Anyway, I'm not going to keep you. If you want to keep watching this, by all means, you can. But if there's no other questions, I will see you guys Monday.